Good morning, class. You're welcome once again to CHM 316 class. And we're continuing with our volumetric analysis or titrometry. We have looked at acid-base titrations. We have looked at complexometric titrations, and we're moving to the third type of titrations, and that is redox titration. I'm sure you're familiar with redox. We know what reduction and oxidation is a full name of redox, and is one of the main types of volumetric analytical techniques. And from the name, it is based on oxidation and reduction reactions where electrons are transferred from the reactants from one substance to another. And the number of electrons that are transferred from one substance to another would help us to know the quantity, to do the qualitative and quantitative analysis of components of many mixtures. So in this topic or this module, we'll be looking at a revision of how to balance redox equations. I'm sure you already know that from your O-level or year one chemistry. We'll also look at the principles of electrochemical cell, a revision of that, and how we can use electrode potential to predict whether oxidation or reduction is occurring in a particular reaction. And also, just like we constructed the titration curves for acid-base and complexometric, we also construct the redox titration curve. Redox titrations are usually, like we know, involve movement of electrons between the analytes of interest that we're looking at and the titrants. And the general principle of redox titration lies in the fact that there is a reaction occurring between reducing and oxidizing agents simultaneously, meaning that the substance that is being oxidized will be converted by an oxidizing agent, and it will become oxidized on the other side of the equation. And we can use this to know the quantity of an analyte that reacts with the titrants based on their chemistry of oxidation and reduction. And many common analytes in chemistry, biology, and environmental sciences can be measured by redox titration. Now, the terminology is, we know that oxidation is loss of electrons, while reduction is gain of electrons. And when a substance gets oxidized, it loses an electron or electrons to move to a higher oxidation state, while reduction, there'll be gain of electrons to give lower oxidation states. And an oxidizing agent is that substance that will take up electron and will get reduced to a lower oxidation state, while reducing agent is that substance that will give up electrons and get oxidized to a high oxidation state. We know, for example, that KMnO4 is an oxidizing agent. It's your KMnO4, your manganese ion. You have manganese 7. Manganese gets reduced from +7 to +2. You can see now that there's a reduction from MnO4 minus, where your manganese is +7, to Mn2 plus. So there's a reduction in the oxidation state from +7 to +2. And when that happens, we can now say that substances that get reduction in their oxidation states are oxidizing agents, and they themselves get reduced. So we know that the old definition, we all know that when oxygen is added to any element, it becomes oxidized. But with respect to redox, movement of electrons, we are all concerned about electrons. So for oxidation, we use the acronym LEO, that is loss of electrons. Whenever electrons are lost, that substance is oxidized. Let's look at the example of sodium that we have on the slide. Sodium has it has an oxidation of 0, and when it gets oxidized, it becomes +1. So it has lost an electron. And anytime that you have a positive charge, it means that an electron is lost. an excess electron, maybe the valence electron on sodium has been lost. So the positive charge here means that an electron is lost. And then you can see now that the oxidation state increased from 0 to +1. So one positive charge means that it is deficient of one electron. It has been calcium to Ca2 plus means that it has been deficient of 2 electrons. Then for reduction, we know from O-level definition that is removal of oxygen, but we're not looking at oxygen in this case. We're looking at the electrons. So gain of electrons is reduction. You can see chlorine here. It was 0. It now becomes minus. So oxidation, chlorine, the chloride ion has gained an electron. So when an electron is gained by chlorine, you can say chlorine has become reduced. So one negative charge means chlorine is enriched by one electron. If you have oxygen, 2 minus means that the 2 negative charges means that oxygen has been enriched by 2 electrons and reduced. So oxidation and reduction in any equation always go hand in hand. So meaning that as an atom is getting oxidized, the other one is undergoing reduction. So when there's an atom that donates electron, there would always be a recipient of that electron that is accepting the electron. So the electron transfer between the analytes and titrants, one is transferring electrons to the other, and the other one is accepting the electron. So oxidation and reduction go hand in hand. Usually then, how do we keep track of this electron transfer? We can make use of the oxidation number or oxidation state. So we usually, a positive oxidation state reflects the tendency of an atom to lose electrons, and a negative oxidation state reflects the tendency of an atom to gain electrons. And like I said before, in a simple redox equation, you have both occurring simultaneously. Let's look at the simple redox equation that we have on the slide between copper and silver. Aqueous silver can be silver nitrate and copper sulfate or copper salt. And looking at this, you can see that the oxidation state of copper changed from 0 to +2. And that of silver changed from +1 to 0. So we have to first pick out the similar species from both sides of the equation. So picking copper now, so this is copper, and the other copper is copper 2 plus. So you can see now that we have Cu2 plus, you have Cu2 plus, copper salt with a 0 oxidation state now being oxidized to +2. Then similarly picking out the 2 silver like species, silver +1 and silver at the 0 oxidation state. So with this now we can pick the 2 reactions, we can see what is happening. For copper, from 0 went to +2, meaning that copper had lost 2 electrons. Copper loses 2 electrons to become Cu2 plus. Then silver also gains an electron to become silver ion. So these are so you have to balance the number of atoms and the number of charges. So here the number of atoms, fortunately, is ratio 1:1 on both sides. So what we need to balance will be the number of charges. Then the next thing we'll do is to balance the number of electrons. So you see here now that for copper, which is reduced, copper was had been reduced from 0 to +2, to Cu2 plus, and silver to 0. So we can now balance them individually. So copper becomes oxidized because it goes from, we remember we said that oxidation is loss of electron. So copper becomes Cu2 plus by losing 2 electrons. Remember the acronym LEO, L-E-O. Loss of electron is oxidation. So copper loses 2 electrons. So copper is oxidized. So this is the oxidation half equation. Copper losing 2 electrons to become Cu2 plus, so from 0 to 2 plus. And let's look at silver. Silver also becomes from +1 to 0. It gained an electron. So silver gains an electron. So gain of electron is reduction. So silver ion becomes silver with oxidation state of 0 by gaining 1 electron. So silver gets reduced to silver, and this is the reduction half equation, and copper gets oxidized. That is the oxidation half equation. So now the next thing is after we've looked at the number of atoms that they balance themselves, copper, 1 on either side, silver is also 1 on either side. The next thing now is to balance the number of electrons, so that, because the two sides must be equal. So on copper oxidation half equation, there are 2 electrons involved. In the silver reduction equation, 1 electron is involved. So we need to, and in our final equation, the number of electrons must not show. So all we need to balance both sides, we have to cancel out the number of electrons. How do we cancel out the number of electrons? Is by multiplying this half equation by 1 and multiplying this by 2, so that this becomes 2 electrons. The oxidation also becomes 2 electrons, and the 2 electrons can cancel out. And in doing that, we also have to multiply. If we are multiplying the reduction half equation by 2, it's not just electrons we are multiplying all the terms there by 2. So therefore, silver becomes 2 moles of silver, the electrons becomes 2 electrons, and silver will become 2 moles of silver atom. So when we do that, the electrons will cancel out on both sides. The electrons on the this side for copper. So when you bring out all the reactant side of both, that is your copper, silver, and 2 electrons on this side, then your reactants, your products, you have your copper, the 2 electrons, and silver. And because in the final equation, we don't want the electrons to be seen, so the 2 electrons cancels out, and you have your final equation. So the final equation, the copper is oxidized to copper ion, and silver is reduced, and 2 moles of silver gets reduced to silver salt. So that is a simple redox equation, whereby you just have 2 simple elements. One is being oxidized, the other is being reduced. Now, let's look at a more complex one, which is an equation we are all familiar with. You did this in 100 level when you were doing redox titration, titrating iron sulfate against potassium tetraisomanganate 7. And remember that in this equation, your iron gets oxidized and your KMnO4 gets reduced. How do we know this had happened? Looking at this iron, remember the first step is to bring out the species that are similar. So we have 2 species identical. We have iron 2 and iron 3. And remember our Leo, our oxidation, there is an increase in oxidation number. Iron is +2 here, becomes +3, meaning that iron has gained an electron from +2 to +3. Then let's look at the reducing half equation. The oxidation state of manganese is +7, and it gets reduced to +2. So manganese is reduced from +7 to +2. So you can see here now that we've identified the oxidation half and the reduction half. The next thing for us to do is to balance, but we know that for us to balance this without looking at the electrons, we first have to balance the atoms. We have 1 mole of iron, 1 mole of iron, 1 mole of manganese, 1 mole of manganese. But on this side, we have oxygen on the reactant side of the reduction half equation, and we don't have any oxygen on the product. So, and we must balance the atoms on both sides. So we have to bring in oxygen to the product side. And the only way we can do that is by, because it occurs in an aqueous medium, we have to introduce water. And with the number of moles of water we introduce will be equivalent to the number of atoms of oxygen we want to balance. And for in this case, we have 4 atoms of oxygen we are balancing, so we introduce 4 moles of water. So now we have 4 moles of water, oxygen is balanced, manganese is balanced, but we have also brought in another element into the equation, and that is hydrogen. We now have 8 atoms of hydrogen. So what do we do to that? We have to balance that hydrogen now. So in balancing oxygen, 4 atoms of oxygen on both sides, we introduce 4 moles of water here. And 4 moles of water has 8 hydrogen atoms. So now we have to bring hydrogen to this other side. And looking at this now, we can see that our equation is balanced. The hydrogen we are bringing, however, is going to be the H plus. So, but that's just to tell us that the reaction occurs in an acidic medium. And I remember when we were doing that titration in 100 level chemistry, you had to add acid to your iron sulfate in your conical flask before the titration occurred. So that acid you were adding in your conical flask is this, that it comes from this. Now, in terms of oxidation number, we now have manganese is +7 here, as you can see. Manganese here is +2. So the next thing is to balance number of electrons. So how do we do this? We have 7 electrons for manganese, and you have 2 on this side. So what do? We need to add 5 electrons. You know, your electrons are negatively charged. So when you have 7 on this side for manganese, what will make this 7 to become 2 is 5. So 7 minus 5 will give us 2. So we now add 5 electrons to the reduction half equation. So now we have the next thing after balancing all the atoms, the electron is now to cancel out the electrons, because like we said, we don't want electrons to appear in our final equation. So bringing what do? The oxidation half equation has 1 electron. The reduction half equation has 5 electrons. So the only way we can knock off the electrons is by multiplying the oxidation half equation by 5. So that this becomes 5 electrons, and we do nothing, absolutely nothing to this reduction half equation, so that the 5 electrons will cancel out on both sides. And in multiplying this by 5, we are, like I said, we are not multiplying just the electrons alone by 5. Every element here that makes up the oxidation half equation will be multiplied by 5, while this remains intact because we are only dealing with the electron. So in doing that, your iron 2 becomes iron 3. I become 1 mole of iron 2 becomes 5 moles of iron 2. 1 mole of iron 3 becomes 5 moles of iron 3. And your 1 mole of electron becomes 5 electrons. And looking at this now, we can conveniently knock off the electrons, 5 electrons on both reactant and product side of the equation. And we now have our final equation having this. So we can see here now that we have 5 moles of ions oxidized by 1 mole of potassium permanganate to give us 5 moles of iron 3 and 1 mole of manganese 2. And this is the full equation. So in terms of moles, 5 moles of iron 2 are oxidized by 1 mole of KMnO4. Remember that KMnO4 was reduced, is the oxidizing agent. So this oxidized iron 2 to iron 3. So, and that is, you should also learn how to balance. We can also balance redox equation in basic medium. So I'll give you that as an assignment to practice, because in exam, you both be balancing equation in both acidic medium and aqueous medium. And I'm sure you've been taught that. So this is just to revise one of them. So try to learn the balancing of redox equation in a basic medium. So we can see the conclusion we have here is that for 1 mole of KMnO4 to react with 1 mole of iron 2, you will need 5 moles of ions. So for 1 mole of this to get this oxidized, you will need 5 moles to react with this to get it oxidized. And that can only be obtained when we get our balanced equation using redox method. So in an experiment that we are working on, where we titrate an unknown sample of iron with KMnO4, you can actually use this equation to calculate the number of moles of your iron, because most likely you will know the concentration of KMnO4. Once you balance the equation, whatever moles of KMnO4 you have, multiplied by 5 will give you the number of moles of iron you are interested in. So this is the equation in the setup of the experiment. You have your iron in your conical flask, a certain volume of your iron, and you know your volume of your KMnO4, you add, and at the end of the day, you have a color change which signifies the endpoint. So you can know your volume of KMnO4 that you have used. And once you know the volume of your KMnO4, you can always calculate the molarity. So the number of moles of your KMnO4 will be the molarity of the KMnO4 multiplied by the volume. Remember that the volume is known by subtracting your final volume from your initial volume. And once you get the number of the volume and you know the molarity of your KMnO4 you have prepared, you can get the number of moles of your KMnO4. And once you know the number of moles of KMnO4, we can automatically know the number of moles of iron. And how do we know it? We know that the equivalence, if you look at where we have, once the number of moles of iron will be 5 times the number of moles of KMnO4, because you have 5 moles of iron reacting with 1 mole of KMnO4. And the moment you know the number of moles of KMnO4, you can infer the number of moles of iron by multiplying by 5 the number of moles of KMnO4. So for this unknown experiment now that we don't know the molarity of our iron, once we know the molarity of the number of moles of KMnO4, we can also know the number of moles of the iron. And this is what will happen. So once the volume of our titrants multiplied by molarity will give us number of moles of KMnO4. And number of moles of iron will be 5 times the number of moles of KMnO4. And once you know the number of moles of KMnO4, you can always calculate the mass of iron. I know that your mass of iron will be the molar mass multiplied by number of moles will give us the mass of iron. So once you know the mass of iron, we can get the percentage of iron in the sample. Once you know the total mass of iron in the sample, this is an experiment you have done before. But we have problem with KMnO4. KMnO4 would always decompose as soon as it is prepared. Is not a it's not a primary standard. You remember when we're talking about standards, we said that we have primary standards, we have secondary standards. Your primary standards are stable. When you prepare a certain molarity of your substance, you are sure that that molarity will be stable. But for KMnO4, it decomposes via this reaction mechanism. It decomposes to manganese oxide and hydroxide ion. So we need to know the precise, so meaning that if you, let's say I prepare 0.5 molar KMnO4, at the time of production, that was what I've prepared. But by the time I want to use it in titrating a redox reaction, I'm not too sure that that 0.5 molar I prepared is still there. It would have decomposed. So I have to first do what we call standardization. I have to titrate my KMnO4 against a primary standard to be able to know the precise concentration of KMnO4. Remember that in this equation, we use the molarity of KMnO4. But for us to be precise in this, we have to be sure that the molarity we have prepared is the correct one that we use to know or calculate the number of moles of iron. So what we do is to standardize the KMnO4 with the primary standard. And the primary standard that we use is oxalic acid. If you remember, go back to your your introduction to titrimetry, said that oxalic acid is a primary standard for redox titration. So we titrate oxalic acid will be stable. So we titrate oxalic acid with KMnO4. So it's also in this case, this is your oxalate ion, C2O42 minus, and it's also being oxidized to CO2. Your KMnO4 reduces to Mn2 plus. And in the same way, we balance equation. In balancing the equation, we have here, we know that you balance the half equation of manganese, also balance the half equation of oxalate. And by the time you balance the electrons, add water on the side of the CO2, once you add 8 moles of water, you have 16 moles of hydrogen. You also balance the electrons and you get this final equation. So from this equation now, we can see here that we need 5 moles of oxalates to oxidize 2 moles of KMnO4. So we can now work out the molarity of KMnO4 that we have prepared. So let's say, for example, we now do the titration. We found out that we have 38.29 mil of KMnO4 that has oxidized the sodium oxalate. We can work out the molarity of KMnO4 as we know from here. And once you now get the molarity of the KMnO4, it's that molarity of the KMnO4 that we now use in this our equation. So the step is that first of all, you standardize your KMnO4 to get the actual concentration of your KMnO4. You standardize with oxalic acid. And once you get your concentration of the KMnO4, you can now react your KMnO4 with iron to get the actual concentration of iron in your sample. So that's with the equation. So this is the oxalate one. So there are 5 moles in the balanced equation. You find out 5 moles of oxalate ion oxidized by 2 moles of KMnO4. So, and this now we can use this also. This is your oxalic acid, and is added. And now your oxalic acid, you add sulfuric acid to give the acidic medium, and KMnO4 is titrated. You get your final volume of your KMnO4, and you can also get the number of moles. And always remember that you have to convert your volume to liters, because we are going to get the molarity. So we can now get the number of moles of your carbonate and the ratio of your reaction. We have 5 moles of oxalate reacts with 2 moles of KMnO4. You can see in the equation 5 moles of oxalate is oxidized by 2 moles of KMnO4. So if you want to find 1 mole of oxalate, it will be 2 over 5 moles of KMnO4. So you want to find the number of moles of oxalate now, is going to be 2 over 5 number of moles of KMnO4. So if you know number of moles of your KMnO4, that will be the 2 multiplied by 2 over 5, will give you the number of moles of oxalate. So, and with that, you can now get your number of moles of KMnO4 is 2 over 5 moles of oxalate. When you multiply that, you get your concentration of your KMnO4. And whatever you get here now is now the molarity of the KMnO4 that actually reacted with your iron. So these are examples of different oxidizing and reducing agents that we have. You have bismuthate, bromate, ferric iron, you have the chlorine dioxide, dichromate is also a popular oxidizing agent. We have iodate, we have iodine, we have dioxygen, we have ozone, we have periodate, we have permanganate, we have peroxydisulfate. So these are the oxidants, and these are common reductants. We have ascorbic acid, sodium thiosulfate, we have sulfur dioxide, thiosulfate. So these are the reductants that we have, and these are the oxidants. And remember, commonly said that vitamin C is an antioxidant because it's always a reductant. So when you talk of taking vitamin C is an antioxidant, it's because it's a reductant in any redox equation. So in KMnO4 titration, so KMnO4 is useful in a lot of redox titration as an oxidant. So, but the most common one of the analytical applications where KMnO4 is used is that of iron. It oxidizes iron from iron 2 to iron 3. It can be used to oxidize oxalic acid. It can be used to oxidize bromine, peroxide, nitrous acid, and many metals, as you can see. So, but the one we're going to use, we'll draw more, is the oxidation. We've looked at the oxidation of iron to iron 2 or to iron 3, and the oxalates to carbon dioxide, to oxalic, from oxalic acid. So now when we talk about redox, we have the electrode potentials of many redox systems, and it depending on the solution where it is prepared. So this is ferric iron. In 1 molar HCl, the potential differs as the acid strength increases. And this is the strongest of them. I can see the strength of the former potential. And for iron 2, in different media, you have different electrode potential. For dichromates, in different media and different concentration of your acid, your potential, as your strength of the acid increases, the potential also increases. So we'll be looking at this later on in detail. So now, how do you prepare the redox titration curve? We need to first, to do this, we have to evaluate the shape of the titration curve, just as we did for acid-base titration, where we looked at strong acid, strong base, weak acid, weak base, and the like. We also note that in acid-base titration or in any complexation titration, the curve shows how the concentration of the hydrozonium ion or the pH changes as the concentration of the metal change. This M can be any of the metals. You can use iron or ferric as an example. So as we can check the electrode potential, which is known by the determination of your pH. So as you're adding your titrants, let's say you're adding your KMnO4 into ferrous sulfate, instead of looking at the color change at the endpoint, we can actually put a pH meter into the solution of your ferrous sulfate in the conical flask. And as you're adding your KMnO4, you can take notes of the concentration of the hydrogen ion. So, but in redox titration, we monitor the titration, the reaction potential instead of the concentration of the species, and we use the next equation to obtain this. So let's look at a titration between a titrant, which is reducing, that is reduced, with another titrant that is oxidized. So A is reduced, A is the reducing agent and becomes oxidized. B is the oxidizing agent and it becomes reduced. So let's say this is our iron. So the A oxidation is the oxidized form of the titrant. The B reduction is the reduced form of the titrant. So let's say this is iron 2 getting oxidized to iron 3. This is manganese 7 getting reduced to manganese 2 plus. And the stoichiometry between the two of them, 1 mole of the oxidizing agent and 1 mole of the reduction agent. So let's assume they have a ratio 1-to-1 reaction. The potential of this, the reaction potential, is the difference between the reduction potentials for each of the half equation. You have the oxidizing half equation. This is for your species B, the oxidation and reduction species, the potential of that, and that of this is the oxidation and reduction potential of A. That will give us the reaction potential, the difference between each of the reduction potential for each of the half equation. Remember that A will have its own half equation, reduction half equation, oxidation half equation, and B will give us, we have the reduction half equation for B. And can have the difference between of them to give us the half reaction, the potential for the overall reaction. So when we add the addition, the titrant to the reaction, to the titrant, there will be a state of equilibrium, and at a point whereby the potential is zero, the equilibrium, the potential at the equilibrium will be zero, meaning that the titrant and the titrant's potentials will be identical. That is at equilibrium, provided, remember, we're talking of if the two of them have the stoichiometry is 1-to-1. So with this now, we can calculate the potential as the titration progresses. And before the equivalence point, that is where the mixture consists of, before the equivalence point, we have an appreciable quantity of the titrant that has not been oxidized will be more in the conical flask than the reduced form. So the unreacted titrant will be very small. And you remember that our titrant is your KMNO4. So we have the next equation is given by this, the net reduction potential, the next potential for the reaction will be the potential of the oxidation half equation and that of reduction half equation for species A, and that would be minus RT over NF ln of the oxidation and reduction concentration. That is for your half equation for A, species A. You can also do that for the B. So each of the half equations, we have their next equation for the titrant and for the titrant. So this is the titrant half equation, and this is the titrant half equation. Let's say your Fe2 plus and your KMnO4. So now let's look at the theory. We'll come back to the next equation shortly. So we want to use this to sketch our reduction titration, redox titration curve. And we want to use a reaction between cerium and iron. Remember that we said we're looking for a redox equation whereby we have the stoichiometry in ratio 1:1. And we look at it here, cerium is reduced from Ce plus 4 plus to Ce3 plus. Iron 2 is oxidized from 2 to 3 plus. So this is our titrant, and our analyte is our iron 2. So let's say in our medium here, we have iron 2 in 1 molar acid solution, which is constantly being stirred, and our burette is dispensing the cerium or the cerium ion. And we put our electrode here to get the potential as each drop or volume of the titrant is added to the titrant. So after the titration, most of the ions in the solution will be iron 3 and cerium 3. This is what will happen at the end of the titration. But these 4 ions that we have here, both the reactant and the product, the 4 of them will be at one time or the other be in this medium. And what will be used to monitor the depletion of iron 2 as iron 3 is introduced will be monitoring the potential difference of the electrode using a calomel reference electrode and a platinum wire. And remember that this will be stirred continuously as the titrant is added from the burette. So now, looking further into this equation, so a redox titration will be set up between this analyte and the titrant. Remember, your titrant is in your burette, your titrant or your analyte is in this reacting vessel. So we have our indicator, the half equation for iron 2 to iron 3. This is the potential. For the reduction half equation, we also have the potential as this. And this potential is in 1 molar HClO4 solution. So we are, like I said before, the steric ion, steric 4 is added from the burette to a solution of iron 2. And this electrode will respond to the concentration of iron 3 and iron 2 equilibrium and cerium 4 and cerium 3 in this mixture as the titration progresses. And we use calomel as a reference electrode. And once the potential is generated here, we'll be able to read the electron voltage. So now for the reference electrode, we have your mercury. This is the half equation for the calomel reference electrode, and this is the potential, the potential for it. But now let's look at the platinum electrode half equation. This is the reference electrode. This is your calomel that contains mercury, and chlorine, and this is the half equation for that. Then for the platinum electrode, we have ion 2 going to ion 3. This is the potential in 1 molar acid. Then we have the reduction half equation. This is the electrode potential. So we can get the net potential by adding the two half equation, your ion 2 and your calomel, to give us ion 2 reducing to ion 3, then Ce reducing to Ce4 reducing to Ce3 plus. So these are the net cell reaction for the reference electrode. So we can actually get the shape of this titration as we are adding. Remember, the cerium is being added. We have a known volume of ion 2, and cerium is being added from the burette. So there are three distinct regions, as you can see in this titration curve. We have the before the equivalence point, which is this part of the curve. You have the equivalence points, and we have beyond or post equivalence points. So before the equivalence points, we know that the analytes, the potential at the platinum electrode is dominated by the ion, because we have more of ion 2. Oxidation has not really taken place. So the potential will be measured at that stage. And as you're adding your cerium ion, the potential increases. Then at in the equivalence point, the potential of the indicator electrode is the average of the conditional potential. That means at that point, you have an equivalence amount of ion 2 and C3 plus and ion 3 plus at this equivalence point. And after the equivalence points, where all the ion have been oxidized to ion 3, is only you have more of a steric ion since there's no more ion 2 that is being oxidized. So let's look at it one after the other. Before the equivalence points, each aliquot of the steric 4 that is added will create an equal number of moles of ion 3 and steric 3, because the cerium gets reduced to cerium 3 plus and ion gets oxidized to ion 3 plus. But as at that time before the equivalence point, we have excess of ion 2, because only a few fraction of ion 2 would have been converted to ion 3. So in the solution, we have ion 2, we have ion 3, we have cerium 3. We won't have this, because as this touches the vessel, cerium gets reduced to cerium 3 and ion gets oxidized to ion 3. So the amount of ion 2 and ion 3 will be known, and we can determine their cell voltages via that method. But the residual amount of cerium 4 is unknown, because cerium 4 is still in the burette that is reacting as soon as it touches the ion 2 solution. So we can, using the next equation that we have before, we can, let me take you back to that equation. This is the next equation that we have. Remember this, that we have the E naught of your reactant minus RT NF ln of the reduction potential and oxidation potential. We'll be needing that equation. So you can see here now that we have this, the potential measured for, this is for ion, and we have your ion 2, the concentration of ion 2 and ion 3. You can find the log of ion 2 and ion 3, and you subtract the standard calomel electrode voltage from it. Going back to that equation, so this is the potential, the standard calomel electrode potential is now subtracted from it. So there's going to be E equals to E plus minus E negative. So this is the next equation for ion 3, going to ion 1 and to ion 2, when it is the oxidation of your ion, and you subtract that of your E minus is your calomel electrode voltage that is measured separately. And that is, so looking at this, we can get our final electrode potential. but we're only going to calculate the potential at the half equivalence point, where you're at that particular point, your ion 2 concentration is equal to ion 3 concentration. So this can be, if this is equal to this, log 1 is 0. So this takes care of this, and your half potential will be given by that. So E half of this value is more or more is for the half equivalence point, and we can subtract that standard Calumet electrode. But in this case, your E positive is equal to the E naught, because we said the log time is 0. So this, your E half, will now be E positive minus E negative. So before the equivalence point, we have this value is obtained for ion 2, this 0.767 would be obtained at before the equivalence points, and you can get the half potential, because this is the whole region of the equivalence point, but this is the half equivalence points. At the half equivalence point, this is where we have equal volume of ion 2 and ion 3 that had not been oxidized. So your E equals to E positive, your indicator electrode, minus the reference electrode. The indicator electrode is the potential generated from your ion 2 and ion 3 pair, and the reference electrode is from the Calumet electrode. And just as we've done before, you subtract this potential, you subtract this from it. This is the constant, and this is the concentration of this, and you get your final reaction. So this is obtained from your E naught that you measure from that equation. Then this is for the potential of your Calumet electrode, and this is your ion 3, this is your ion 2. And when you simplify this, you get that. But we said that at the half potential, where your ion 2 equals to ion 3, this will be equal to 1, and this will be 0, and this will now give us the E, and that will be this minus this, and that will give us that value. So, and this point where half of the potential is obtained, we can, is also the same thing that we use when we're doing acid-base equation, when we say pH equals to pKa in acid-base titration. So we can also do that for the cerium, just as we've done for iron. At that particular point, this will be this is the half potential. You see 3 plus equals to C 4 plus. And we can get the logarithm of that. And that would also give us its own electrode potential. So you can bring the two together, the oxidation equation and the reduction equation. Bringing the two together at equilibrium, we now have all the 4 species present at equilibrium. So we have more of ion 3 and cerium 3, and a few fraction of cerium 4 and ion 2 in the mixture as equivalence point. So this is the reaction we have. Cerium gets reduced, iron gets oxidized. And I can also calculate the reaction of the potential at that particular point. So at the equivalence point, you can we don't need concentration of iron 2 or cerium 4, because this is already being converted to iron 3, and this is the unreacted cerium that has not gotten reduced. So we can't solve either of these two equations independently, but we have to add 2 of them together. This is for iron, this is for cerium. We add 2 of them together to get the overall electrode potential at equivalence point. So when we add them together, get this value. So this also will also be 0, because if this is equal, the 2 times are equal, this will be 0, and you can get the electrode potential at equivalence points, adding the two of them together. So that's your inflection point, the middle of the steepest portion of the curve. So when you get this now, this is your calomel electrode potential, and this is your reactant potential. When you subtract the two, you get the voltage. So at this point, this is the voltage, the potential that we monitored. Then we have the post-equivalence point, and that would be, you have more of your Ce4 plus, because the iron 2 is all oxidized to iron 3. And you have iron 3 and cerium ion, and we have excess of cerium 4 in solution that has not reacted. And you can also calculate that also, and subtract the reference electrode from it to get your final electrode potential. So when you simplify that, you get that. So the titration depends on the ratio of the reactants, but is independent of the concentration or volume. So this independent of the volume, but we are looking at monitoring the potential of it. Unlike the acid base where we're looking at the volume, we're now monitoring the potential as the electrons oxidized or they get reduced. So in summary, bringing everything together, and this is, you have to note this, before the equivalence point, we have your iron 3, which is the potential of iron 3. This is your reference electrode, and this is your next equation ratio. If you're looking at this, you get our reaction potential before the equivalence point. And like I said, if this is 1, this will be 0, and you can get your electrode potential. In at equivalence points, we do that for the both pair of the oxidation half and the reduction half. We add the two together and we'll get the potential of that as well, subtracting the reference electrode from it to get the E naught of the cell. And the post-equivalence point will just be that of cerium, because that is what is remaining in the species. And we subtract that, we get our final this reference electrode from it, we get the electrode potential of the equation after the equivalence point. So in summary, the greater the difference in reduction potential between analytes and titrants, what is being analyzed at the titrants, the sharper will be the endpoint. And also the voltage at any point in this titration depends only on the ratio of the reactants. And we know that prior to the equivalence points, the half reaction involved the the analytes is used to find the voltage, because the oxidized form of the reductant, the reduced form and the oxidized form of the analytes are not known. Then after the equivalence point, it is the excess one there will be the titrant, which is your cerium ion. Now, how do we find endpoints in redox titration if we are not, apart from using the electrochemical measurements of using the reduction, the potential of the cell? So we know that already, that we can use electrodes, just as we've seen in sketching the titration curve. We could also use indicators. So we have two major ways. We use electrochemical measurements, that is using the measuring the potential, using electrodes, your reference electrode or your standard electrode. And we also use indicators. We call them redox indicators. So what are these redox indicators? They are chemical compounds that undergo color change as it goes from its oxidized form to its reduced form. And it is very well similar to acid-base indicators, where in acid-base indicators, the color will change as the protonation occurs to on the indicator. Because and so for redox titration, there would also be a color change in the indicator as indicator changes from one form or to the other, either from the oxidized form to reduced form or from the reduced form to the oxidized form. And if the titrant is highly colored, the color may be used to detect the endpoints. So there are some, however, that are self-indicators. And an example is the KMNO4. KMNO4, when we do KMNO4 titration, we don't add any indicator whatsoever because the titrant or the titrant itself is its own indicator. We know KMNO4 is a deep purple colored solution. And when it is reduced to Mn2 or 2 plus, there will be a change in the color. So it will be reduced from when it is oxidized from KMNO4 is deep purple. And when the Mn7 manganese 7 get reduced to Mn2 plus, the color changes to pink when it is reduced. So we don't need any external indicator to tell us that reduction are taking place to KMNO4. So that's why we say it is self-indicated, it is a self-indicator. So during the titration with KMNO4, the purple color of KMNO4 is removed as soon as it is added because it is reduced to Mn2 plus. So when you have your KMNO4 from the burette, as you drop it into the conical flask, that purple color disappears because if you're, especially if you're titrating with a clear solution, a colorless solution. So as KMNO4 drops into that solution, what happens is that it gets reduced to Mn2 plus and it becomes colorless. But as you are adding it, it gets to a point that a drop of excess KMNO4 would not find any titrant to react with, and that will now leave it with a definite pink color, meaning that at a point in time, as the KMNO4 is dropped into the iron solution, the KMNO4 color disappears, but a time comes that there is no more iron to get oxidized, and what we have will be excess of KMNO4, and that KMNO4 will have nothing else to react with, and that will now, there'll be a color change, and that color is indicating that the reaction is complete. And the endpoints in KMNO4 titration does not occur at the equivalence point, but a fraction of a drop beyond it. That is why, and that's towards the endpoint, you add it dropwise, so that just one drop that will change the color, that will not react with any titrant, will show that the reaction is complete. Apart from that self-indicator, so we said we looked at, we can use electrochemical indicators using your electropotential. We could also use a self-indicator, and we also have what we call redox indicators. Redox indicators are colored dyes that are weak reducing or oxidizing agents that can be oxidized or reduced. So they are dyes, they are organic dyes that can either be oxidized or reduced. And how do we know this? The color differs when it is oxidized or when it is reduced. So the colors, once the color changes, we know that, and the indicator has become oxidized or reduced. So the potential at any given, the oxidation state of the indicator and its color will depend on the potential. Comparing with acid-base indicators, it works with the potential and it determines the ratio of the two colors. So you can see here now that your ferroin, and this is an example of indicator redox, is called ferroin. In the oxidized form, ferroin is pale blue, and in the reduced form, it is red. So once the color changes, we know that it signifies the end of the reaction. So these are examples of indicators, and they also have their own electrode potential. We now phenolphthalein, colorless at the reduced form, red oxidized. We have indigo methylene blue, diphenylamine. We have so many of them. The ferroin is commonly is called ferroin, but the name is tris 110 phenanthroline iron, but it's commonly called ferroin. So these are different types of indicators and their colors in their reduced or oxidized forms. Then we have specific indicators. Some indicators will form a colored compound with a specific oxidized or reduced form of the titrant or the titrant. Some of them are selective and specific. An example of them is starch will form a dark purple complex with iodine, with iodate. So we can use this color to signal the presence of excess iodine as a titrant, because the color will change from colorless to purple. Iodine is purple. So when you add starch, the color will change to purple, and that will show the completion of the reaction, meaning that all the iodine has been consumed, and the color will change from purple to colorless. Another example is thiocyanate. It forms the soluble red complex with iron in the presence of iron 3. So these are specific indicators used in redox titration. And the most important class of indicators are substances that do not participate in this redox titration. So they don't participate, just like your acid-base indicators do not participate in your titration, but their forms, in their oxidized or reduced forms, the color will change. And when a redox indicator is added to the titrant, the color that is impacted depends on the solution's potential. So as the solution's potential changes, as you're adding your titrant, the indicator would also change its color, and the oxidation state will change, and that will tell us that an end has come to the titration. We can also use the relationship between potential. We can use the half equation to do this. This is the indicator oxidized form. This is the reduced form, and number of electrons involved. So we can also use the next equation as well for the indicator, the oxidation and reduced form, using the next equation. And if we assume that the indicator color changes from 0.1 to 10, then we can find the range, just like we did for acid-base titration, that it changes on a scale of 1 to 10. And look at the pKa of 0.1 to 10. We also find the potential with which, the range with which the color change can occur, using that next equation. And color change for redox indicator occurs mostly over this range of this. So where E naught is the standard reduction potential for the indicator, and N is the number of electrons involved. So color change for redox indicator occurs over a potential range. So we can see now that it's substituting for ferroin. Now this is the potential for ferroin. So we can substitute that into redox, the next equation, to get the concentration, and it's plus or minus this. So it is within this range. And subtracting that of the standard calomel electrode, you can also get this range when you subtract 0.241 from this range of value that we have before. That will be 0.847 to 0.965 volts. That is the range at which the electrode, that the ferroin as an indicator, will change its color. So if you look at using ferroin here, say the range is for this ferroin in oxidized form will be blue, reduced form is red, and at this electrode potential, and in this titration curve, look at the electrode potential is approximately that value. So with this now, when we subtract the calomel electrode value from it, we'll get something close to 1. So we want to look at common redox reagents, and a very common one is starch. Starch is just your cellulose, just like the starch you use in your laundry or that is consumed as food. And we use it for titrations that involve iodine. And how is this possible? Is because starch forms a very reversible complex with iodine. It will form a very dark blue color. And this color reaction is very sensitive to small amounts of iodine. So when titrations of reducing agents with iodine, the solution will be colorless up to equivalence points. Then when an excess of the titrant is added, the solution will turn to blue, because it's very sensitive to small amounts of iodine. So when you are titrating and you have iodine in solution up to equivalence points, it will be colorless. But as soon as you have excess of iodine, starch would form a complex with that iodine that had not reacted, and gives and imparts a color that signifies an endpoint in the reaction. So starch, you see, is your cellulose. When it reacts with your iodine, it forms a complex. So as you can see, starch is not an indicator, but it reacts to the presence of iodine. So once you have an iodine that is not reacted, it will complex with starch, and you now see your iodine bound at the center of the starch helix. So this is your the helix is formed with the starch, and you see your iodine at the center. So this is your iodine chain with your cellulose chain of starch with iodine, and that will give you the color when you have your excess of iodine that has not reacted with your starch. So iodine can be used as so we can see that iodine dissolves. Iodine can be used as an oxidizing agent in the reaction. This is iodine that becomes reduced, so it's an oxidizing agent. And iodine will dissolve slightly in water to form triiodide. When iodine reacts with iodide ion, it will form triiodide reaction. It will form triiodide. So when you have a solution of your iodine, to form your triiodide, you just add your potassium iodide to iodine in water, and that will now give us triiodide. And we have two types of reactions that involve iodine. We have what we call iodimetry, and that is the reducing analyte, whereby a reducing analyte is titrated directly with iodine, and that will produce iodide ion. Then we have iodometry, where an oxidizing analyte is added to excess iodide ion to produce iodine, which is now titrated with this thiosulfate solution. So iodimetry is the direct titration whereby you're reducing analyte titrates with iodine to form iodide. Iodometry, your oxidizing analyte is added to excess iodide to produce iodine, which is now titrated with standard thiosulfate solution. We look at them one after the other. So now your acidic solution of iodide, remember we said that your iodide is your iodine with potassium iodide will form triiodate. So this is your triiodide, triiodide is unstable because the excess iodide ion is oxidized by air. You can see your iodide is your triiodide is a mixture of iodide and iodine. And this your iodide is unstable and it is oxidized by air to give your triiodate. So as in neutral solution, oxidation is insignificant in the absence of heat, light, and metal ions. But the triiodide can disproportionate to hypoiodous acid, iodate, and iodide. We look at that later on. So what we do is to prepare standard triiodide, you add your potassium iodate to small excess of potassium iodide. Then you add a very strong acid to produce iodine. So these are different reactions of iodimetric titration, whereby, remember we said that iodimetry is when your iodine is titrated with a reducing analyte. So the reducing analytes here, these are different types of species that we can titrate, and we use triiodide, which is your iodimetric titration. So for example, for arsenic, this can be titrated with sodium hydrogen carbonate with iodide. And we can monitor the using iodine, the oxidation of iodine there to get the endpoints, and the color change using starch will help us to know the whether the endpoints of the reaction are taking place. These are examples of reactions that involve iodide ion. This iodimetric is with triiodide. Iodimetric, then we have iodimetric titrations, and these are the examples of iodimetric titration. So let's look at them one after the other. In iodimetry, so that iodine is a moderately strong oxidizing agent that can be used to titrate reducing agents. And so this is your analyte that you don't know. Your titrant is your iodine, which is a oxidizing agent to now produce your iodide. And the titration with iodine as an oxidizing agent is called iodimetric analysis. It is usually performed in neutral or mildly alkaline pH. The standard iodine is used as a titrant for an oxidizable analyte. It is called iodimetry, which we've said before. The analyte, which is your reducing agent, will react with iodine to form iodide. Your analyte, your reducing agent, reacts with iodine, the oxidizing agent, to form iodide. An example is your of iodimetry is the titration of ascorbic acid. You know that as vitamin C or ascorbic acid is an antioxidant, which is a reducing agent. So it oxidizes to iodine will oxidize it to produce dihydroascorbic acid. When iodine oxidizes, becomes dihydroascorbic acid, which is readily soluble in water. And we can use this titration to determine the concentration of vitamin C in fruits or drugs. Now to iodometry. This is an indirect titration whereby an excess of iodide. Remember, in iodimetry, we use iodine. In iodometry, we use iodide. So excess of iodide is used to quantitatively reduce a chemical species while simultaneously forming iodine. So the excess iodide react to the reducing species to form iodine. And this iodine, and remember that just like we talked about with the back titration, you have excess of iodine. So this iodine now is later on titrated against potassium thiosulfate to now produce iodide. So we start with iodide, you titrate with your reducing with your sample, and your sample gets oxidized, and iodine is produced. Then the iodine that is produced here is now related to the amount of the analyte originally present in your sample. This iodine now can be used to titrate thiosulfate to now get your iodide ion. So the detection of endpoints in iodine titration, the indicator that is used for titrations that involve iodine is starch. And the color change due to starch complex at the endpoints helps us to know when the reaction is complete. Because like I said before, starch will form a dark blue complex with iodine. So the endpoint of iodimetry will correspond to a sudden color change to blue. Remember, in iodimetry, iodine gets reduced to iodide. So that iodide, the color change with starch will be blue, and that tells us that the reaction has been completed. In iodometry, there'll be a loss of that blue color. So in iodometry, the starch is added only after the color due to iodide has begun to fade. So in iodometry, we don't add the starch, and we don't the color. We don't add starch at the beginning of the titration. Is by the time you are doing the second titration with the thiosulfate, you add starch because the starch can be destroyed in the presence of excess triiodide when you start your experiment. Remember, for iodometry, we use excess of starch. but we use excess of iodine or triiodide at the beginning of the titration, but you don't add your starch. After you have titrated the beads and you get a pale straw color, then before you add your starch and you now get your endpoints. So hydrogen peroxide, which is an oxidizing agent, can also react with iodide, which is to in iodometry, using according to redox titration. This is your peroxide, this is your iodide, and your peroxide can be reduced to water and iodine, and your iodide gets oxidized. So in the first portion of the experiment, a sodium thiosulfate solution is prepared and standardized with potassium iodate. So potassium iodate reacts with the excess iodide in acid solution to yield triiodide. So first of all, we first standardize your potassium, your sodium thiosulfate is a secondary standard. So the first step is to standardize it against a primary standard, which is potassium iodate. Then this potassium iodate reacts with the excess iodide to yield triiodide, which is now titrated against this standardized thiosulfate, because the iodide here, the triiodide here, is what is reacting with your hydrogen peroxide. And after the reaction is complete, the iodine produced is titrated with sodium thiosulfate, and you can now work out the concentration of your iodine here to know the amount of iodine that actually reacted with your peroxide. So reactions involving iodine can be used for the analysis of moderately strong reducing agents by reacting iodine in iodometry or using excess iodide in iodometry. Unlike iodometric titrations, in iodometry, two reactions are involved. Iodometry is just a direct titration with iodine, but in iodometry, we are going to titrate with excess iodide and sodium thiosulfate. So this is just the difference. In iodometry, the analyte is the reducing agent, one reaction step, and the standard solution is iodine. In iodometry, the analyte is oxidizing agent like your peroxide. We have two steps of reaction, and the standard solution used here is sodium thiosulfate. So you have a practice question for you to do, and I want you to have a try of that question. Thank you.